I ran into a rather surprising application of derivatives of inverse trigonometric functions long ago when I was studying rainbow formation in relation to teaching physics. And first of all, before I even go anywhere, I want to thank Eric Rolfe for this photograph. He published it under Creative Commons attribution, share alike, and so I'm very happy to put the attribution here. I got this off of Wikipedia. It's a beautiful example of a rainbow with a variety of interesting phenomena here. There's more to look at than just a rainbow here. Um, Let me lead you through a little tour first before we really get into the math. Let's try to appreciate what you're seeing when you see a rainbow. Notice the primary rainbow is multicolored. Red is on the outside. The inside is the violet. Notice the red is sort of a sharp boundary, whereas the violet, it just sort of fades away. Notice that on the inner boundary there are some little banding that goes on here that's different from the regular spectral colors. This is more similar to what you get on an oil slick. These are interference colors here on the inner edge here. Notice there's a secondary bow out here and that the colors are reversed. Notice that the sky appears bright inside the main bow and it appears considerably darkened outside the main bow, and it's actually darker between the two bows than it is either outside the secondary or inside the primary. So this is the darkest band here in the sky. It's as though the light has been robbed out of part of the sky, which is then shown in the bows themselves. You have enhanced light here and you have depleted light elsewhere in the sky. That's sort of an interesting concept. Notice that the photographer, at the very bottom of the picture, there's the shadow of the head of the photographer, and that's the center of the bow, which means the sun is directly behind the photographer's head, and when you're looking in this direction, you're looking at what's called the anti-solar point. So the rainbow is formed as a circle surrounding the point directly opposite the sun. Okay, enough for that. Let's go into looking at the question of how are these rainbows formed. And I'm going to start by focusing on the primary bow, although the same kind of analysis can lead you to the secondary bow. One of the questions we're going to ask along the way, by the way, is why is the bow of the size that it is? What's the angle between the anti-solar point and the bow? And it turns out it's always the same. It's a fixed angular separation between when you're looking in this direction and when you're looking in this direction. Okay, so those are some of the questions that it would be nice to be able to understand, and a little bit of math and a little bit of physics goes a long way to help answer these questions. Okay, rainbows are formed by water droplets, and we're assuming that they're essentially spherical. So tiny water droplets drifting through the air after a rainstorm. And you have to have water droplets in the air, and you have to have sunlight. And so it can't be that you have an overcast sky or clouds blocking the sun. But once the rain storm is essentially over, typically you get clear spots, and if the sun comes through a clearing, it's going to shine on water droplets, and the light's going to scatter back basically toward the sun, but in a cone. All right, now these drops are all over the sky, at least wherever it's been raining. And if you're standing over here and you're seeing a droplet that's out here, you're seeing light scattered to your eye because you are standing inside this backscatter cone. Now, it turns out that the backscatter is limited to a certain angle, and that's what we're going to actually want to find using our newly acquired skills with calculus. Okay, but this angle is out to a certain point here, and the angle is slightly different depending on whether you're talking about red light or blue light or violet light, whatever. And so the angle of this cone is larger for red light wavelengths than violet, and therefore you're going to get a red cone and overlapped with this violet cone. Let's see how this backscattering of light due to an individual water droplet here ends up being a rainbow. And the answer is it's not one water droplet. It's many, many water droplets, each one sending light in a particular direction. So the water droplets all over the sky in here are inside the bow, and the water droplets out here would be outside the bow. If you take a water droplet that's in a particular angle, notice that along this dashed line, any water droplet anywhere along this line is going to scatter red light back to your eye. Other water droplets that lie in this line will scatter this violet light back to your eye. And water droplets inside the bow, we're getting white light scattered back. Water droplets that are outside the bow, all of that light is being scattered somewhere else, and we're not part of that. And so the sky is going to look darker out here because there's less backscattered light in this part of the sky. So that's one of the things we observed. Another thing I mentioned about the photograph was that the red had a fairly sharp boundary, and the violet edge of the bow had sort of an indistinct boundary. The reason for that is red light is being scattered all the way from this outer red boundary over to this red boundary. Okay, so you're getting red light throughout this larger cone. You're getting violet light throughout this smaller cone. And so whereas the red light you're getting is pure, the violet cone is being contaminated by white light because you're getting the reds and the yellows and other colors are overlapping with the violet. And so you're not getting a pure single monochromatic color there. You're getting various degrees of white light mixed in that increase as you go towards the violet. So it's sort of smears out when you get to that edge. Let's move on a little bit. How far away is the rainbow? Well, notice that the rainbow is made from droplets that are at many different distances, some of them very close to your eye, and it can be very far away. You can generate a rainbow simply with a sprinkler. And so you set up a lawn sprinkler and you're looking at droplets that are very close to you between you and the lawn, and you'll see the rainbow that appears to be between you and the lawn. But you also have these droplets from way out here. You actually are not looking at a particular circular arc in the sky. What you're looking at is the edge of a cone. So a rainbow is really a cone of light. So from your eye, which is the vertex of the cone, if you look out along the edge of the cone, you see these spectacular colors. If you're looking inside the cone, you see generalized white light scattered back, which gives the sky sort of a enhanced, bright appearance to it. And notice that it's at all these different distances simultaneously, and they all line up. So from your point of view, this is an arc projected against the sky. So there really is no pot of gold at the end of the rainbow, because there really is no end of the rainbow. It would be a cone traced on the surface of the earth somehow. Okay, so let's get to the question, why does the sunlight, when it hits a water drop, scatter out only as far as a particular angle, and what is that angle? By the way, we have a secondary bow as well. I'm not going to spend time on that, although we could do a parallel kind of an analysis and look at that. But there's actually a second cone, and this is actually forward scattered light. So the light that hits the droplet here, some of that light is scattered forward, and it's only back as far as this angle on either side. So I'm not really going to go into the derivation of the secondary bow at the moment, but it could be understood in very much the same way as our analysis of the primary bow. Okay, so let's just worry about the primary bow for now. Okay, here is a diagram showing sunlight entering a raindrop, and it enters across the entire surface of the raindrop. And notice what happens to the light. The light comes to the surface of the drop and it bends. This is due to what's called the law of refraction. It's determined by Snell's law. This is a piece of physics. It's really the only piece of physics in this demonstration that I have to supplement that's not part of our course. There is a relationship between the angle of incidence and the angle of refraction, it's called. So how much this light bends when it crosses the surface from air to water is what determines this angle. Now, some of the light goes on through the droplet and just comes out the other side. However, some of the light reflects back when it gets to the back surface of the drop, and of that light, some of it continues out of the drop once it goes over here. So a fraction of the light that enters the drop will reflect once and then come back. Those are the rays that form the primary rainbow. Let's just go to this example. There's another possibility is that the light hitting the drop might reflect twice inside the drop and then leave. It turns out that less light follows this path, and then you can also have it continuing to bounce multiple times. So a lesser amount of light would bounce 3 times, and a lesser amount of light would bounce 4 times, etc. The brightest of these beams that form bows, it turns out, are the first 2, and the brightest of all is that primary reflection that only bounces once. So we're going to follow what happens to that ray. So consider the light that goes straight into the raindrop. The light that goes in and reflects once would come straight back out. As I take light that hits further and further to the side, it turns out that it refracts at this surface and it reflects at this surface and refracts again an equal amount over at this surface. And it turns out, interestingly, if you just look at this, I have the computation done following Snell's law here, and notice that there is a maximum angle. Okay, so if you calculate what is this deflection angle as a function of what's called sometimes the impact parameter, how far off-centered this beam is hitting the drop, then it turns out that function goes through a maximum and then comes back around again. And it's at that maximum angle there, that's what's going to determine the boundaries of this cone. So we could have light on both sides. You can have light, this red beam of light is scattered everywhere within the cone, but only out to a certain maximum angle, and then it turns around. Okay? And it was really I discovered this phenomena for myself. Of course, many other people have studied this, but I found out this for myself when I was playing with a little lucite disc on a light table at the Exploratorium, which is a famous museum, a hands-on science museum in San Francisco. That's the basic overview. And so now what we want to do is look at what Snell's law says and calculate what the angle is, and then see if we can calculate the maximum angle. The way we can do that is we're going to find what is the angle of deflection as a function of the angle of input over here, the angle that we're off to one side, and then if we're going to see that that function which gives us deflection as a function of the input angle is a function which has a maximum. And so if we differentiate it and set it equal to 0, that gives us the turnaround point in the function. And that's how we're going to find that maximum angle. Okay, let's look at, say, a swimming pool or a fish tank or something. This is water, and up here is air. And if you take light that strikes the surface of the water, this angle here between the ray and the vertical, this by the way is called the normal. the normal to the surface, which is the perpendicular line to the surface here. And if this is theta, then it's going to bend in such a way that it comes in closer to the normal inside this denser material. Okay, so call this theta 1 and this theta 2. All right, so theta 2 is going to be smaller than theta 1 if this is denser material than this. So if this is a vacuum ideally, and this is some other material, we get the maximum amount of bending there. Air is pretty close to a vacuum for our purposes here, and so we're not going to make a big distinction there. Okay. The particular material determines a constant, which is usually referred to as n, which is called the index of refraction. It turns out n is also dependent on the wavelength of the light, so we can come up with different values of n for the red and the violet, which is why red and violet have different behavior. Okay? So, when you have this situation, we have the angle of the light measured from the normal as it hits the surface, and we have the angle of the light measured from the normal inside the surface. We can say the sine of theta 1 over the sine of theta 2 is equal to n. Okay, that's assuming you're moving from air into, or from a vacuum, either one, into this material. Okay? Now, I'm not going to try and justify this. This is a result of the analysis in physics. So take a physics class and you'll run across Snell's law, S-N-E-L-L apostrophe S. And so Snell's law is given by this formula. Okay? We're going to use Snell's law to derive our rainbow angle. Okay, here's a diagram. I laid it out using Geogebra so it could make it accurate. Okay, so this is what we're calling theta 1, and this is what we're calling theta 2. Notice that we have here an isosceles triangle. So this also is theta 2. And here the light reflects off the back surface of the water, and it reflects at equal angles. So this as well is theta 2. And this is an isosceles triangle, so this is theta 2. When it exits the water, it bends using the same relation as when it entered. So this is theta 1. Okay, so that's the basic path of the light. Now, let's do a little bit more geometry here. Notice that we're taking the incoming ray here as parallel with this axis that we've established. And so the angle here, theta 1, corresponds to this angle. When I think of this one and this one as parallel lines, these are corresponding angles. So this is theta 1. The overall angle between this incoming ray and this outgoing ray is indicated back here, and I'm going to call that angle delta. And so this angle here is delta over 2. And notice that that angle is the same as this angle. This is delta over 2. Because this line is parallel to this line, and these are corresponding angles again. So theta 1 plus delta over 2 add up to what's an exterior angle for this triangle. Okay. So this angle must equal the sum of the two different, depending on your geometry course, this is called the opposite interior angles or the remote interior angles. The two angles that are not this angle that's right next to it. Okay. So this angle here is the sum of these. So theta 1 plus delta over 2 adds up to 2 times theta 2. Solving for delta, first there's delta over 2, is 2 theta 2 minus theta 1. Doubling everything, I get delta is equal to 4 theta 2 minus 2 theta 1. Okay. Now that we can put, that's the geometry that we need. We're going to put that together with a little bit of physics we have, which is Snell's law. and we'll be able to come up with delta as a function of theta 1. So by specifying where we enter the droplet, we should be able to see the angle of deflection between the entry angle, like this angle here, but between the incoming ray and the outgoing ray. All right? So here's delta as a function of theta 1 and theta 2, but we know that sine theta 1 over the sine theta 2 is equal to n from our physics. From this, we can get that the sine of theta 2 is equal to sine theta 1 over n. All right? Just bring the n down here and sine of theta 2 up, and I just flipped them around. Okay. Or theta 2 is equal to the inverse sine of sine of theta 1 over n. Okay, and this I'm going to substitute in here. So delta is equal to 4 times this relation minus 2 theta 1. All right, so we now have delta, our deflection, as a function of our entering angle here. Let's look at this function in GeoGebra before we proceed. All right, here's the view of this function in GeoGebra. I put it as f of x, and instead of theta 1, I put x. I'm taking the domain here as being between 0, which is the ray coming in central to the drop, and at pi over 2 is where it's tangential to the drop. So somewhere in between there, you're going to get the maximum deflection. Just crudely, if I were to try to locate that, let's do this. Let's go down to the tangent line. And notice that if I find the place where this is maximum would be the place where the derivative would be 0. Okay? So at least in this particular function, that would give us our way of finding this peak value here. So that's the goal. We're going to take the derivative of this function and set it equal to 0 and use that to try and locate this maximum point. Okay, so let's start. So d delta d theta 1. We have two terms, so we take them one term at a time. So this is 4. The derivative of the inverse sine, that we've learned how to do. It's 1 over the square root of 1 minus this thing squared, that 1 minus x squared, except the x here is this whole argument. So sine theta 1 over n squared. Okay. Then applying the chain rule, we have to take the derivative of the argument. The coefficient there is 1 over n, and the derivative of the sine of theta 1 is the cosine of theta 1. That's it for the first term. The second term, the derivative here is simply minus 2. Okay. Now, having taken the derivative, we want to take this and set it equal to 0, because that's how we locate that top point on the curve, as we just now saw. Okay. So let's start simplifying this. This first business here looks like 4 times the cosine of theta 1, and there's an n that we can bring down here, and a radical of 1 minus the sine squared of theta 1 over n squared. That's this. Taking care of that, taking care of that. Okay, minus 2 equals 0, or bring the 2 to the other side. This is simply equal to 2. Let's divide both sides by 2, and this becomes a 1. Let's take this denominator now and multiply it up to the other side. And so we have 2 cosine theta 1 is equal to n times the square root of 1 minus the sine squared theta 1 over n squared. Okay. Now, let's square both sides. So we have 4 cosine squared theta 1 equals n squared times 1 minus sine squared theta 1 over n squared. Okay, let's distribute in this n squared, and we get n squared minus, this cancels here, so I simply have sine squared theta 1. And let's bring the terms with theta to the same side. So 4 cosine squared theta 1 plus sine squared theta 1 equals n squared. Okay, in order to combine these into a single term, I'd like to change the sines into the cosine or the cosines into the sine. Let's take this cosine squared and rewrite it as 1 minus the sine squared. When I multiply it by 4, it's 4 minus 4 sine squared theta 1 plus sine squared theta 1 equals n squared. Okay, here's one of them minus 4 of them is minus 3 of them. Minus 3 sine squared theta 1. 4 minus that equals n squared. Let's bring this to the other side. So I'll say plus 3 sine squared theta 1. And bring this n squared over here. So it's 4 minus n squared is equal to 3 sine squared theta 1. Bring the 3 down here. Take the square root. And that gives us the sine of theta equals that. Let's take that to the next page. Okay, from this we can evaluate theta 1. This would be the angle theta 1 that would give us 0 for the derivative. So this would give us our maximum deflection. That's really not what we're looking for. We want to find the maximum deflection, but this is the step along the way. Okay, what we need is a value for n. So this comes out of physics by experimentally looking at how much light bends from various wavelengths. You can come up with a value of n for the color of the light and for the medium, whether it's water or glass or whatever it is. And so this is all tabulated due to a lot of experimental work. Okay, so that's the physics of it there. So looking up the index of refraction for red light, it's approximately 1.331, and for blue light, or violet light I should say, n is about 1.343. Okay, so this is an approximate span for the visible part of the spectrum. Okay, so using these values of n, we can come up with values of theta. But theta is really not what we're looking for. We want delta. Let's go back to here, and this gives us delta as a function of theta. So really, this is what we want. Let's take a copy of that and put it over here. So here's the agenda. We're going to calculate values of theta 1, then I'm going to plug in theta 1 here and find the corresponding delta. So our goal then is to find delta for the red and the violet ends of the spectrum. We'll see what those turn out to be. Okay, I've entered the two values of n for red and violet right here. So the 0 register has the red version, and the register 1 has the violet version. Okay, let's stick with red all the way through and then come back and do it again for violet. Okay, so starting with n for the red, let's recall the value of n, which is the 1.331 here. I'm going to square it. I'm going to change the sign. I'm going to add 4. Okay, so that's inside the numerator. Divide by 3 and take the square root. We get 0.86. That's the sine of theta 1. So if I take the inverse sine I get 59.5267. I'm going to store that in register 2. Okay. I'm now going to use that number. I'm storing it there because I'm going to need it twice in the next calculation. So that's my angle theta 1. The sine of theta 1 is that divided by n. So recall my 0 value of n there. That's my red n. And hit divide. And then take the inverse sine of the result. Okay, times 4. And then subtract 2 times theta 1. So recall theta 1, which is register 2 there, is 59 degrees-ish, times 2, and subtract. And it comes out 42.369, 42.37. So 42.37 degrees would be the angle of the rainbow for red light. Let's do it again for violet, and that ought to come out, we're expecting, somewhat smaller. Let's see if it does. So if I recall my violet version of the index, I'm going to square it, change the sign, and then add 4 to it, and then divide by 3, take the square root, and then take the inverse sign, and so I get 58.83, which is somewhat smaller for that, but that's not the angle we're looking for. I'm going to store that in register 3 this time. Now I plug that into the delta equation. So take this same angle, take its sine, divide it by n, so recall the blue version of n and divide, and then take the inverse sine times 4, and then recall theta 1, which is that, times 2, and then subtract this from the other term. I get 40.65, let's say. All right? So, this is our angle for the rainbow. So these are the angles from the center line, which is the anti-solar direction, out to the rainbow as measured from the observer's point of view. And somewhere between 40 and 42 would be the range of angles for the different colors. Okay? There is a very concrete actual application of taking the derivative of an inverse sine as part of an overall calculation. You've also seen that in order to successfully do calculations, especially in physics problems and things like this, where the difficulty of the problem is governed by the real-world situation, you just have to plug away at it and keep your scratch work very neat. Take plenty of space, go back over and over and check your work as you go. And you learn painfully the long hard way to be careful in your calculations, and not that you'll never make errors, but that you'll catch your errors because you need to check this line by line as you go. Otherwise, you end up with a big mess and don't know where to turn. So, we've figured out the angle of the rainbow. If you start with the geometry, just as we did for the primary bow, and you put an extra reflection in, it turns out it's not that much different to figure out the angles for the secondary bow as well. But I'll leave that as a project for anybody who's ambitious enough to tackle it. Okay?